So welcome to yet another molecular design lecture. So far we had been discussing small molecule design, both the rational and the random parts, and now the time has come to move on to large molecular design. So when we talk about large molecular designs, as usual we can divide this into the rational and random parts. So we can divide this into the rational and the random parts. But there is another way to talk about it as well. Now the large molecules that I will be talking about could be proteins and peptides, could be nucleic acids, it could be other kind of structures, for example carbon nanotubes being one of them, but I will not be discussing those in this lecture. So now when we talk about designing protein, peptides or nucleic acids, the techniques used for each of these molecules are quite different. So within each of them, whether it's proteins or nucleic acids, of course we have the rational and the random part. That part is fine. But the way to design protein molecules and the way to design nucleic acid molecules, or carbohydrates for that matter, are so different from each other that it's better to divide them up according to the type of molecule which you are thinking of designing as well. So I will begin this series of lectures with the rational design of proteins, then move on to the random synthesis, and then come over to nucleic acids, again follow both the rational and the random synthesis approaches. Now when we talk about peptide or protein design, some very important theoretical work which led to the foundation of rational design of peptides was done here in India by Professor Gopal Samudram Narayana Ramachandran and his group, mainly his students Vishwanathan Shashishekaran and Chandrasekaran Ramakrishnan, here in the University of Madras. Now the work done, the Ramachandran plot, of course you are quite familiar with it, I understand, having studied it in various courses. As you already know, it's of extreme importance in various fields of biochemistry. For example, it is used in structure analysis, it is used in structure evaluation, and of course structure designing, both for proteins and peptides. So I think being Indians, and because of its tremendous importance, it is important to study the Ramachandran plot, particularly in relations to peptide or protein design, in some detail. So I'm going to cover the various aspects of the Ramachandran plot in a series of 4 videos, starting with this one, in which various aspects, the general aspects of the plot, as well as its applications in various fields, will be covered in some detail. Now this would be over and above whatever I had already taught about the Ramachandran plot in the molecular modeling section of this course. So since we are going to do it in some detail, for the sake of completeness, I might overlap with the molecular modeling portion a little bit, but we will be doing all that and moving much forward out here. So when you think of proteins, particularly protein structures, the first thing that comes to mind is the tremendous diversity of protein structures that you have. You have, for example, structures that are largely helical, structures that have a huge component of beta sheets. Indeed, there are some proteins which without hardly any helices, mostly beta sheets. And then some others out here which contain a mix of helices and sheets. And even then, you have helices, you have sheets, you have turns, you have coils. But the arrangement of these different secondary structures into the tertiary structure of the molecule is so diverse, so different, that it's very difficult to believe that the similar principles can guide the evolution or the structure formation process. Now, are there any such universal principles that guide structure formation? And here comes the concept of the Ramachandran plot. But before we can go into the details of the plot, it's important to take another look, a fresh look, because we have looked at it before, on aspects of molecular modeling. Again, some of the things which I'm going to talk about now, I had already covered in a previous lecture, and doubtless you would have learnt it in other courses as well. But I think it's important that we start from the beginning and take a look at these concepts once again. So the first thing that we are going to talk about is how to represent a molecule in silico, that is in a computer. Now there are two main types of doing this. One of them, as I had spoken about before, are the so-called external coordinates. So in which what you do, you set up a Cartesian coordinate system, O, X, Y, Z, a rectangular Cartesian coordinate reference frame, and you place your molecule in it. So each atom is considered to be a massless, volumeless point, but which has a coordinate triple, xi, yi, zi, I being the ith atom, referring to the ith atom, which specifies its position in space. So all the atoms in the molecule are specified by its own coordinate triple, right? And then we have a list of connections, which are the bonds, which tell that which atom is connected to which bond. So these are the basic requirements of the external coordinate representation. Now the position of the molecule and the orientation of the molecule with respect to any reference frame is of course given by these coordinates of these individual atoms. Now there is of course other alternative ways to describe a molecule, generally going by the name internal coordinate systems. And there are of course many ways to define a molecule in the internal coordinate space, but perhaps one of the most popular one goes something like this, that if I have a diatomic molecule, again as I said, that the atom is considered to be massless or volumeless. Therefore, the only parameter which characterizes a diatomic molecule is the distance between the two atoms, which we will call the bond length, and here I show it with the letter L. This is all that is necessary and sufficient to describe the structure of a diatomic molecule. Now, if I have a 3-atom molecule, a triatomic molecule, then of course I have two bond lengths, L1 and L2 out here. But that is not enough, because the orientation of the two bonds with respect to each other needs to be specified. And that of course is done by the angle theta. Now one of the things when you talk about a diatomic or a triatomic, etc., and we call them internal coordinates. The reason we call them internal coordinates is that there is no external frame out here which specifies the molecule. So whatever parameters we are going to talk about, they are within the molecule, they are internal to the molecule, and therefore these are called internal coordinates. Now again, to refresh ourselves quickly, for a diatomic we just have a single parameter, that is the bond length L. For triatomics we have three parameters, two of them are bond lengths L1 and L2, and the bond angle between them, the bond angle theta between them, which specifies how one of the bonds is oriented with respect to the other. So these three parameters are necessary as well as sufficient to describe a 3-atom molecule. Now what happens if we have 4 atoms? Now of course again, as usual, we have 3 bond lengths, L1, L2, L3, and we have 2 bond angles, theta 1 and theta 2. But that is not enough. What we need, something called a torsional angle, which we call it chi out here. So this is an extra parameter that we need. Now what is this torsional angle? To understand that, the torsional angle, or its another name is a dihedral angle, sometimes we call it. Dihedral angle also. Technically there is some difference between a dihedral angle and a torsional angle, but in much of the literature that I have seen, people use these two terms interchangeably and they mean the same thing with it. So we will also use these two terms, dihedral angle or torsion angle, interchangeably and not distinguish between them. Although some textbooks very correctly make a slight distinction between these two, but we will not get into this at the point. So now to define a dihedral angle or a torsion angle, we need 4 atoms. So let us say I have my 4 atoms out here, A, B, C and D. Now there is a standard result in geometry that in 3-dimensional space you can define a plane, you can always define a plane that passes to 3 points which you specify beforehand. So if I have these atoms A, B and C, which are 3 points in space, the atoms being considered massless and volumeless, so therefore they are just points. So I can pass a plane which goes through this, which is shown by this color out here. Similarly, I can pass another plane through atom B, C and D, which is shown by this color. Now these 2 planes, they need not be coplanar or embedded in a larger plane. They can have an angle between them, and that particular angle out here is the dihedral angle or the torsion angle. Now we call it dihedral angle. The word dihedral, the word hedron, from which it comes, in Greek refers to a plane and sometimes to a face as well. So like you have a crystal face or something like that, so which is also a plane, of course. So that's often called a hedron, in Greek, and from which the word dihedral, that is the angle between 2 planes. And the word torsion comes out here because any changes in this angle can be brought about by rotation over the BC bond. So to specify that particular rotation, we sometimes call it the torsion angle also. Now one way to see the torsional angle is that it's an angle between 2 planes. Another way to look at it is that if you look at down the BC bond, if you just you bring your eye out here and if you see it from here this way, then it will look something like this. So the atom B and the atom C will now look on top of each other, while the atom AB bond and the CD bond will be projecting out. Now from this projection, the angle between the projections is also the same angle chi, which you can realize if you imagine that you are looking down this plane, then you can only see these 2 bonds, while this one is hidden one on top of each other. The angle now will be the angle between the projections. Fine. Now of course, since the angle can vary, it can vary between minus 180 degrees passing through 0 and then going back to plus 180 degrees. Now the angle being a periodic thing, minus 180 and plus 180 refer to the same angle. So the question is, what is 0, what is minus 180 or 180? There has to be some sort of a definition. Yes, indeed there is. So if I have 4 atoms all in one plane, so I assume that they are all in the same plane, and the atom A out here and the atom D are on opposite side of the BC bond. In that case, we will call this angle 180 degrees. And if again all the 4 atoms are in the same plane and the atom A and the atom D are on the same side of the BC bond, then we will call that the torsion angle is 0 degree. So you can imagine that is that if this 4 atoms with these 2 planes is considered like a book, and if it is fully opened so that the pages are flat lying on one plane, And then of course the atom A and atom D would be opposite to each other, and this angle will be 180 degrees. And then again, if I close this book, right, close it on top of bring this page on top of it, this page. So bring this plane on top of this plane. So again, all the 4 atoms are in the same plane, and atom A and atom D are on the same side of the BC bond. Therefore, the angle is 0 degrees. So we have to keep this in mind. So we have now defined chi is equal to 0, chi is equal to 180. What about intermediate values of chi, in which these two planes are not on coplanar, but there is an angle between them? To understand that, we will have, I make use of this particular animation. So again, in the center, I imagine that I have my 4 atom system, which is oriented somewhat like this. Okay, and the atom which is closer to you, I keep it fixed, pointing straight up, and the atom which is further away from you, I am rotating in a clockwise sense. Now in biophysics, the clockwise direction is considered to be positive. So when these 4 atoms are in a plane, and this atom is exactly in front of the other atom, so I have chi value as 0 degree. And then as it goes around, goes this way, it comes opposite, it becomes 180 degree. Then since 180 and minus 180 are the same thing, so it moves from minus 150, minus 120, etc. until it comes back once again at 0 degree, when the 2 atoms, the red and the yellow atoms, are completely eclipsing each other. So that's how the angle is defined. Now IUPAC, that is the International Union of Pure and Applied Chemistry, they define certain names for regions of this angle. For example, if the angle is torsion angle is between minus 30 to plus 30, this region, we call it syn periplanar. If it is negative, we'll call it minus syn periplanar, or minus SP for short. And if it is positive, we'll call it plus syn periplanar. Then again, if it is between 30 to 60 and 30 to 90, we will call it synclinal. Again, plus synclinal, minus synclinal. Then between 90 to 150, we will call it anticlinal. Again, plus anticlinal, minus anticlinal. And then from minus 150 through 180 to plus 150, this region is called anti-periplanar. Again, minus anti-periplanar, plus anti-periplanar. So this is the IUPAC nomenclature. Now there is an older nomenclature which is neither complete, somewhat confusing, but nevertheless is ruling all everywhere. So every article or research paper that you see defining a torsion angle, you often see, most often you see the older nomenclature being used. Now this nomenclature is somewhat inspired from double bond isomerism. So if I consider a double bond, I can have a double bond like this, right? And we will call it cis double bond. So this region, when it is more or less around 0 degrees, there is no well-defined limits out here. So if it is somewhere close to 0 degree, we call it cis. And if it is in the opposite direction, that is like this, it is somewhat similar to a trans double bond. So this region is called trans. Now please understand that one should not confuse this with cis-trans isomerism, because in this particular case there is a double bond in between, right? So therefore it is rigid. But since the bond is rotating and all that, the torsion angle is always defined over a single bond, not a double bond. So it's freely rotatable. The words cis and trans are just lifted from the double bond case and probably not being used very correctly. And what happens if it is neither cis nor trans, if it's something in between? So if it is around plus 60 degree, we call it plus gauche, and if it is minus 60 degree, we call it minus gauche. No clear terms are there for the anticlinal side, so it is not even complete. But nevertheless, since this is very popular, so we have got to know it. Now when you come to peptides, let us see what are the torsion angles involved in the peptide backbone? So here is a peptide backbone I have drawn. Now if you go through this backbone, you see there are three kinds of torsion angles. The first one, which is defined by the carbonyl carbon out here. So you have the carbonyl carbon, then you have the nitrogen, which is the carbonyl carbon, then you have the nitrogen, then you have the C alpha carbon out here, okay, and then you have the next carbonyl carbon. So these four atoms define a torsional angle, and we call it the Phi torsion angle. Then I have another torsion angle out here, which is defined by the nitrogen, the C alpha, okay. So I have the nitrogen out here, then I have the C alpha out here, and then I have the carbonyl carbon out here, and then the next nitrogen, right? So these are the four, and this one is called the Psi torsion angle. And lastly, if I start from C alpha, so I have C alpha out here, then I have the carbonyl carbon out here, then I have the nitrogen out here, and then the next C alpha atom. So this particular torsion angle is called the omega torsion angle. Now the entire backbone is specified by these three torsion angles. Turns out further that the omega torsional angle, which is about the peptide bond out here, because of the partial double bond character of the peptide bond, is fixed. It does not rotate so much. So this is most of the time omega is around 180 degrees. It is in the transposition or anti-periplanar position, and it remains so. So whenever we talk about the backbone conformation, we can to a first approximation say that the conformation of the backbone is a function of just two torsion angles, phi and psi, because omega is constant. Now you can say that, well, the bond lengths and the bond angles are also there. Indeed they are there, and they are also important. But again, there is hardly any variation in the bond lengths or the bond angles. The bond lengths remain almost absolutely constant for the most part. The bond angles, of course, can move about a little bit, and that has important consequences, and we will discuss that also. But again, that motion is very small, so very largely, so we can approximate that the backbone conformations of a peptide is just a function of the phi and the psi torsion angles. So this is about the representation and analysis of this. I think I should make also this clear again, that the backbone conformation is a function of the phi and psi torsion angles. Now the second concept that we are going to talk about is something that we already discussed when we are talking about physics-based scoring function for molecular docking, and that is this concept of van der Waals energy. Now what is this? If we have two atoms which are not bonded, that is, they are part of either different molecules, or even if they are part of the same molecule, then they are connected to each other through at least 3 or more bonds. That is, they are not interacting through each other through bonds. In such case, we find a certain kind of interaction between them. This interaction arises out of some fluctuating dipoles, which arise because of the moving electron density around the atoms, and which causes them to attract each other when they are at a somewhat larger distance. And this attraction increases as the distance is lowered between the two atoms until there comes a point when it is maximum, and then it suddenly reduces and in fact becomes a very strong repulsion. That is, there exists some point in which the atoms, instead of attracting each other, start repelling each other. So we can think of these atoms as somewhat like hard spheres. So let's come to this first. So these spheres, they attract each other, but as the distance is reduced, and there exists some kind of a cutoff point out here, beyond which they are just about touching, and then of course they do not further attract, instead they repel each other. You cannot push them further in. So Ramachandran looked at this kind of van der Waals interaction and made it even simpler. He made what is called the hard sphere approximation, in which he considered that there are two atoms, which are not bonded of course, beyond a certain critical distance, just do not interact with each other, so that there is no kind of interaction, no attraction, no repulsion, nothing. And then comes, as you are reducing the distance between them, then comes a cutoff point beyond which they just repel each other, and they're like infinitely strong repulsion force. Effectively, that means that we consider this. He considered these two atoms like very hard spherical objects, like glass marble or a steel ball or something. And if they are far apart from each other, they just don't interact. But when you bring them closer, and there's a point in which they touch each other, and then you cannot push them any further, right? So if you try, then it will be repelled very strongly. So Ramachandran and his group then set about to find out what exactly is this cutoff distance for different non-bonded atom pairs. And when they were doing it, they realized that, well, actually, it's a little bit more complex. That for the most part, there exists a cutoff distance, maybe 90% of the time, there exists a certain cutoff distance, but about 10% of the time, that cutoff is violated, and you can go a little bit further. So as if the atoms are not absolutely hard, but they are kind of like tennis balls. Like you can bring them to the touching point, but you can push them a little bit, you can squeeze it a little bit. Now these distances, which are these two cutoffs, this is the normal limit, which is true for most of the atom pairs. And then they have this extreme limit, which is a small number of atom pairs to show this. So this they measured out by looking at crystal structures of small molecules which were available at that point of time. During Ramachandran's time, there were very few structures of peptides, long peptides or proteins were known. But there were quite a few small structures, maybe dipeptides, amino acids or other molecules whose crystal structures were known, so they could measure those distances carefully. So like that they derived these values of this normal limit and then this extreme limit. And this was done for different types of atom pairs, could be hydrogen or hydrogen, hydrogen, oxygen, so on and so forth, and which are not in a bonding interaction. So here are the values of the normal limits and the extreme limits that they got. And if you notice that the normal limits are slightly larger than the extreme limits. So for example, for hydrogen and hydrogen, the normal limit is about 2 angstrom, and that's about the touching distance. But you can squeeze them a little further, you can come down as low as 1.9 angstrom, but not lower than that. Similarly, for say carbon and carbon, the normal limit is about 3 angstrom, while the extreme limit is again slightly less at 2.9 angstrom. So like that, they defined this distance limits. Now, having done that, they go back to their peptide. In fact, they instead of using a long peptide, they use a very small peptide model. So essentially, this is one amino acid. In this case, I show alanine, whose amino and the carboxylate groups are blocked. So the amino group is blocked with acetyl group, and the carboxylate group is blocked by the N-methyl group. So chemically, we might call it acetyl, alanyl, and methyl amide. But they use a much simpler nomenclature. They called it simply the alanine dipeptide. Now, why dipeptide? Because it had 2 peptide linkages. So this is one of them and this is the other. and you had the amino acid. So if you see out here, so by our definition of phi and psi, that there is about the alanine residue, there is a single phi and psi, and there are two omegas, omega 1 and omega 2, let's call them. But we have also discussed that the omega angle is always fixed at around 180 degrees. So therefore, the entire conformation of this molecule is a function of the phi and psi only, right? And there's just one phi and one psi, unlike a large protein where every amino acid other than the ones at the N terminus and the C terminus will have its own phi and psi. So here is the geometry of this molecule. So you can see these two peptide planes on the two sides of the alanine amino acid, and the phi and the psi angles are also shown. Now, having set up this system, what they did computationally, in fact, at those days they didn't have computers in the sense that we know it today. They didn't have electronic computers, but they used to do these calculations on mechanical calculators. So which just I think could only add and subtract. So there was a lot of hard work which was done, I think particularly by C. Ramakrishnan, who was the PhD student at that time. So anyway, so with that they set up this system, and then they varied the phi and psi atoms, taking care that no non-bonded atom in this system ever approach each other at a distance which is lower than this limits. Okay, so once they did that, so they plotted all those conformations in the phi and psi space, and they found something like this. So here they had, so you can see this clear thing. So they had a fully allowed region where none of the atoms out here, non-bonded atoms, they approach each other at a distance which is lower than the normal limit. So they had 1 and 2 fully allowed regions, and then they had this partially allowed regions, which is one big one here and some here also, in which at least one or maybe more atom pairs were approaching closer than the normal limits, but even then they did not violate the extreme limit. And then there was a lot of space out here which they called disallowed region, in which there was at least one pair of atom which was violating the normal or violating the extreme limit. They are definitely violating the normal limit. It's also violated the extreme limit. To see this in some detail, let us look at this situation, where what I did is that I generated alanine dipeptide conformations with phi and psi specified from this map, and then I plotted those atoms which are crossing the extreme limit. For example, in this particular region of the map, I find that the C beta carbon and the oxygen, the carbonyl oxygen, they approach each other very closely, and they violate the extreme limit. Therefore, this region is not allowed. In this region, again, I find the C beta atom and the NH, the hydrogen atom out here, they are coming too close. In other regions, I find here I find like two oxygens, the two carbonyl oxygens from adjacent peptide bonds, they are bumping into each other, or sometimes as we call them a short contact. They are making a short contact, a disallowed contact, that is the distance between them is lower than the extreme limit. In some regions, more or less in the center of the plot, there are just more than one pairs which are bumping into each other. So all of these bumps make this region disallowed. But in the normal or the extreme limit, in this, the peptides are fine. There are no bumps or short contacts between them. Essentially, it meant that all conformations of the alanine dipeptide can have phi psi values which are just within these regions only and nowhere else. And since you can consider a large protein or a peptide made up of many such residues, all of which have to be within this region. So this was the first major universal constraint which Ramachandran and his group discovered. That is, all the amino acids in a protein can have phi and psi values strictly within this so-called allowed regions of the plot, right? Maybe the normally allowed or the partially allowed, and they are not supposed to go outside that region. If they go out, there is going to be a short contact which is strongly disfavored and therefore not allowed. So this is true for every protein, every peptide that there exists. In order to make it more easily understandable to you exactly what I mean by the short contacts, I have made a little animation which might make things a little bit clearer. So here goes. So here what you see on your screen is the alanine dipeptide molecule. So this part out here is the acetyl group CH. This one represents the methyl carbon CH3, the carbonyl carbon, and the oxygen CH3CO. And here is the amide. So you have the amino group alanine, amino group of alanine, and this is the C beta atom. This is the alpha hydrogen atom, and then this is the carbonyl carbon. This is the oxygen. And then of course the N-methylamide blocking. So again I have a nitrogen, and I have a hydrogen, and I have a methyl group. So this is the standard alanine dipeptide. Now the Phi angle out here is defined by these four atoms. Number 1, 2, that is this carbonyl carbon, the nitrogen, the alpha carbon, and then again the carbonyl carbon for the N-methylamide. So this here, the value of the Phi angle is around minus 180, and the Psi angle is defined over this particular bond, and here I have kept it at 60 degrees. So you can see these are the four atoms, 1, 2, 3, and 4. So this has been kept at approximately 60 degrees. Now having set up this molecule in this way, what I can do is that I can rotate any atom or bond which I want. So what I decide now is that I will rotate the Phi angle, keeping the Psi angle fixed. So, and at the same time what I will do is that I will measure the distance between this carbonyl oxygen and this hydrogen. Now look at this, these two atoms are considered non-bonded because even though they are part of the same molecule, there are a number of bonds between them. So 1, 2, 3, 4, 5, 6. The 6 bonds between them, which is too many. So we would consider them not interacting with each other. So we can take this particular non-bonded pair and measure the distance as we vary the Phi angle, keeping the Psi angle constant. Let us see how it looks like. And here goes. Now, as you can see immediately, as the Phi angle is rotating, which is keeping the rest of the molecule fixed, but the acetyl group is actually rotating along with it. And as it rotates, the distance between the oxygen and the hydrogen that we are monitoring is undergoing a lot of change. So it is sometimes going as high as around 4 to 5 angstrom, and when it is the smallest, it is maybe lesser than 1.5 angstrom. But this short distance is clearly below the extreme limit, right? So this particular oxygen and the hydrogen atom is sometimes violating the extreme limit at certain values of Phi, and at other times it is not violating at other times, right? So this is what we mean by the short contact. That is a particular conformation in which two non-bonded distances become very close to each other. Now, why is a short contact so bad? Why is it disallowed? Right? To understand that, what we can do, we can switch on the van der Waals radius of all the atoms. And as you can see that when the distance becomes very small, this oxygen and the hydrogen atom are just overlapping. Now you know one thing, that surrounding the atomic nucleus there is this shell of electrons, right? So when two non-bonded atoms, they come so close to each other that these electron shells are overlapping, there is going to be tremendous electron-electron repulsion, which is why this particular conformation will not be allowed, right? Because the electrons will be repelling each other. And that is why certain conformations where the distances between the two atoms become very short, very small, these are not allowed because of electron-electron repulsion between their non-bonded electrons. So this is in a nutshell what exactly I mean by short contacts. I hope this has been clear to you. A main essential features of the Ramachandran map. In subsequent lectures, we are going to look at how the concept of allowed regions, etc., for one amino acid, how does it affect the conformation when I have a larger peptide, right? So we are going to look at those kind of situations, and then we are going to see certain cases where these apparent allowed regions which you see here are sometimes violated, and if they are violated, why they are violated, how they are violated, that is what we are going to see. Finally, we are going to look at this from a design point of view, is that can we, by using special amino acids, sometimes artificial unnatural amino acids not found in proteins, but if we bring them into peptides, can we modify the map in a way we want, so that thereby we can set up conformational limits onto our designed peptides. So all of this are going to come in the subsequent videos. So stay tuned. In the meantime, stay happy and stay safe.